Okay, Professor Wang, I have made you also the co-host.
Okay.
So you can open your presentation slides once I'm done with the with my only slide that I want to share.
Okay.
And I can also do that for you. You can just see there's a share screen green button on the bar.
Yes, I did see that.
So you can do that after I just open the talk. Yeah.
Sure.
I'm going to let you know.
Okay.
So let's admit everyone and. Well, okay, it's 3 o'clock sharp. We have a few people joined to the webinar. First of all, hello, everyone. Hope you're having an awesome day so far. We are having another round of SNAS webinar series, and we are delighted to be joined by Professor Wang from University of South Carolina to present his recently published article with us in the Journal of Western Applied Sciences. He was kind enough to accept our invitation, and today he is here to give his talk about the research. I am Amin Fatemi, and today I'm going to host this webinar and help handle the webinar. I'm the managing editor of engineering at SN Applied Sciences Journal. And yes, Professor Wang is here today with us. I just want to ask everybody to please mute yourself at all times and also close your videos at all times. I think that privilege is taken away by the software, but just in case you have to open and have a discussion at the end of the meeting, you can do that at the end. But other than that, you can present your questions in the chat box. Let me introduce Professor Wang. He is an associate professor at Department of Mechanical Engineering, University of South Carolina. He completed his PhD at Carnegie Mellon University in 2005 and obtained his Bachelor's of Science and Master's of Science from Shanghai Jiaotong University in China in 1998 and 2000 respectively. In the period from 2005 to 2017, he has held several positions of increasing responsibility at the CFD Research Corporation, Huntsville, Alabama. His research interests focus on computational and data-enabled science and engineering, including reduced order modeling, large-scale and/or real-time data analytics, system-level simulation, computer vision, and cyber-physical system and autonomy with applications in aerospace, unmanned systems, manufacturing, and biomedical devices. He has published over 100 papers in international journals and conferences. So, Professor Wang, I'm going to hand it over to you now.
Okay.
And please go ahead with sharing your screen and take it away from here. Thank you very much.
All right. Thank you. Thank you very much for introduction, Amin. Can everyone see my screen?
I think so. Okay,
great. All right, nice. Okay, so first, it's a great honor to give this presentation at SN Applied Science. So the title of the talk today is the DEIM reduced model constructed by the hybrid snapshot simulation. This is the work done by my student and me. I would say in the last few years, and then my student just defended last month. So it's a congratulations to him. All right, so this is the outline of my talk. First, I will give a brief introduction and the background in what we are doing and why we do this. And then, of course, I assume, not every audience, is working on reduced modeling. So I will give a little bit of fundamental introduction about reduced modeling. And then I will present our methodology, hybrid snapshot simulation for DEIM ROM construction. I will talk about the hybrid snapshot simulation, proper orthogonal decomposition, and incremental singular value decomposition, model switch, and DEIM, and finite volume implementation. All right. And this will be followed by the case studies for numerical heat transfer models, and then results and the discussion. Finally, I will conclude the talk, and then of course followed by question and questions, right? All right. So the background. So in the past, I would say in the past decade, various reduced modeling techniques have been developed for physics-based numerical simulations. So why? Because a lot of times in speed, time-sensitive applications are strongly desired. All right, especially in the scenarios where the computing resources is very limited, reduced model will be more even useful because the demands for computing resources of the reduced model will be very low. And almost basically I would say almost all the reduced models are based on the subspace projection. All right. So basically, these animations and also these figures basically shows some work in our group in the past 10 years. Basically, we have developed a lot of reduced models along this area in these areas, like convective heat transfer in microfluidics, spacecraft thermal analysis, aerosolvable electricity, and also aeroelectricity. All right. And then if you are interested, you can visit our website, and then you should be able to find the details about these publications. So there were two kinds of challenges that we plan to address in this paper. The first one is ROM, basically, just like a lot of machine learning techniques, you still need to have something called a training simulation or snapshot simulation. In our community, we call it a snapshot simulation. All right. So in other words, you need to first run some snapshot simulation, time-consuming offline snapshot simulation. Then you can generate this reduced model. Then you can apply this reduced model for online verification simulations, for other simulations in real time. So number one challenge, you still need to run some snapshot simulation, which is like a training simulation, in order to generate this reduced model. And then the second challenge is a lot of times the nonlinear reduced model is not computationally efficient, okay, which will be discussed later. I will explain why. In general, linear ROM will be extremely computationally efficient, but the nonlinear ROM is not. All right. So now let's go to the next one. So now let's take a look at the state of art. All right. So this slide first. In this slide, I want to introduce some relevant. Sorry for that, the typos. Be relevant previous efforts. All right. And then if you look at this, one area which is directly relevant to this research is the adaptive snapshot simulation. All right. For example, Ali et al. Presented adaptive snapshot simulation along with error estimation and convergence analysis in order to make the snapshot simulation more efficient. Wang et al. Proposed parallelized the snapshot simulation, which divides the snapshot simulation into multiple threads so that that can be run in parallel. And also Oxbury presented adaptive snapshot data selection to reduce the time and the memory usage in proper orthogonal decomposition. All right, that's the first category relevant to the present research. And the second relevant efforts is hybrid modeling method, combining full order models and reduced models, or method of skipping steps. For example, Rapon and Tergani presented a hybrid method that alternate the simulation will alternate between full order model and the local reduced model, to make the simulation faster. And the form also, Professor Katz's group presented full order model, adaptive dimension reduction, and the ROM construction approaches, and also online model order reduction by selectively skipping time steps during form simulation. All right. So that's kind of like the second category relevant to our research. And the last category, which is actually is a very, even more broad category, is efficient parametric and the nonlinear run. Parametric means that you have a reduced model within a high multi-dimensional parameter space. You want to cover the entire parameter space. In other words, your reduced model is parameterized, right? So several methods have been proposed to address that problem, like reduce the basis, local basis update, and the locally weighted basis. And the second challenge, as I mentioned in the previous slide, is nonlinear reduced model, which in general is not computationally efficient. So to address that issue, a lot of approaches, like for example, Gauss-Newton with approximated tensors, DEIM, discrete empirical interpolation method, and the missing point estimation have been proposed to specifically improve the computational efficiency of a nonlinear reduced model. However, according to the best of our knowledge, so the hybrid snapshot simulation to accelerate hybrid simulation method that combines full order model and a reduced model for hybrid snapshot simulation has not been proposed. So that's basically the motivation for our research. We want to use the hybrid snapshot simulation to reduce the computational cost associated with the ROM generation. And the second thing is that we haven't seen any approach that have demonstrated, of course, the hybrid snapshot simulation for DEIM ROM. All right. So then the second aim of this research is to investigate the feasibility of hybrid snapshot simulation to generate DEIM ROM. DEIM means discrete empirical interpolation method. All right. So that's kind of like the purpose of this research. All right. So in the next slide, I will give a very brief introduction about what do I mean hybrid snapshot simulation. So if you look at this one, all right. So the first step, this basically is the snapshot simulation, which is the first stage, training simulation. As I mentioned in the previous slide, in order to generate ROM, you need to have a snapshot simulation, right? So what we have done is basically we divide this entire simulation into many intervals, delta t, like in this, right? So for example, you have 100 seconds, the total simulation for the snapshot simulation, the time for the simulation, snapshot simulation time is 100 seconds. You can divide them into 10 intervals, and then each interval is 10 seconds. However, here, this delta t is not the time step for the simulation. This delta t is only the time, the duration, the period of the interval. All right. So then for each interval, each interval can be simulated by the full order model or the reduced model. All right. Look at this. This blue curve represents the interval of full order model. The red one represents the interval of the reduced model. So within this full form interval, we will do three things. First, we will compute a full order model, of course, right? And the second one, we will compute this POD modes on the fly. I will explain what is POD modes, proper orthogonal decomposition modes. Okay. Of course, we will also accumulate a snapshot data of the nonlinear term. That will be associated with the DEIM, which will also be discussed later. All right. So in the red curve, that is the reduced model interval, we will do two different things. First, of course, we will compute reduced model, right? So to cover this period. And the second one is to reconstruct and accumulate the snapshot data of the nonlinear term, which again is associated with the DEIM, and I will discuss about it later. All right. However, at the end of this snapshot simulation, we will compute the POD modes of the nonlinear terms UN. This POD modes of nonlinear terms UN will be different from the POD mode UR. UR is a POD mode for the solution variable. That is something I want to emphasize. All right. And then we will, at 2, we will also do DEIM to determine the interpolation points. Okay. And then, of course, at the end of the step 2, we will have these DEIM interpolation points, and then we can construct the very computationally efficient reducible model DEIM or DEIM reducible model that can be used for online verification simulation or online testing simulation, which is the time you really want to utilize the reduced model you just generated. All right. So this slide gives you an overall picture of this hybrid snapshot simulation method. All right. As I mentioned, we need to go to the details of the reduced model. I want to give you some introduce some fundamentals of a reduced model. So now let's look at this governing equation, right? This is the ODE set. Y is the dependent variable. T is time. All right. We can separately consider two kinds of nonlinearities. One is called the intercell nonlinearity. For example, like transport phenomena. Let's say for example heat flux, right? When we talk about the heat flux, typically we need to calculate the gradient between the current my current location and my neighbor, the temperature solution at the neighboring solution, because this is a gradient. So we call it an intercell. The reason I call it a cell because in finite volume is control in finite volume method, this control or discretized volume is a cell. So in other words, this term will involve at least two cells, depends on the order of discretization. The second one is called a cell-wise nonlinear component, which has nothing to do with the solution in my neighboring cells. In other words, for example, the heat source, right? The heat source, let's say the heat source only depends on the local temperature, and then it has nothing to do with the temperature at my neighbors. So in that case, we will have this cell-wise nonlinear term, right? In general, this cell-wise nonlinear term is very easy to handle, okay? But however, the intercell nonlinear transport term in general is hard to address. All right, now we have the original equation. Next thing we want to reduce its dimension. As I mentioned, most of our approach is based on subspace projection. Now let's think about this. What is the subspace projection? So a lot of times this is why, for the physics-based, partial differential equations, that, when we try to solve it, they are not random. They will not, be distributed everywhere in the solution space. Typically this is why, is a vector, right? So because, think about this, if we are solving partial differential equations, this is why, after the spatial discretization, this will be an ODE set. Then this Y will be a vector, right? And then when you solve this ODE set, you will find that your solution typically is not random. It will not go everywhere. It has its specific trajectory. All right. So let me give you an example here. For example, this is the three-dimensional parameter space, right? This is a three-dimensional space, for Y. Y is a vector. You have the first component, second component, and the third component. However, if my solution, the trajectory of my solution is within this orange subspace line. You see, like it is in a plane, here. That means the solution space actually is only two-dimensional. Okay, you don't really need to have three variables to describe your solution. You actually only need to have two variables to describe your trajectory of your solution, right? So in other words, we can, correlate the original three-dimensional space with the two-dimensional space using a transformation matrix, which is UR, okay, here, right? So for this example, UR will has a dimension 3×2, right? Because in this YR subspace, you only have two variables. Original Y has three variables. So then you only need to have a transformation matrix, which is 3×2. All right. So in other words, you can save one dimension. All right. However, unfortunately, a lot of times in order to calculate this subspace, you need to run this snapshot simulation in order to calculate this UR, this projection subspace. All right, that's the reason why Y-ROM will not come for free. You have to run a snapshot simulation to get this UR first. Okay, now let's say we do find this UR transformation, then we can project this equation, okay, onto this subspace. Then we will get this equation in the middle here. All right, and then we will use a test orthogonal normal subspace UR again, and then basically we will do a transpose UR left multiply UR transpose on both sides. Then you will get a reduced equation here. Now you can see that basically UR now this is only has a dimension of 2. You need to solve 2 equations. But however here original Y has 3 variables. You need to solve 3 equations. But now you only need to solve 2 equations, right? Think about this. If you have a large problem, this Y can be something like 1,000 to 1 million. However, if you can find this transformation matrix UR, and then you can reduce this solution the number of the solution variable YR to something like 10 or 20, then you can significantly accelerate your computational speed. So that's the idea of the reducer model. Okay. Now, let's take a look at this nonlinear term here, right? So think about this. If F is linear, which if it is linear, then F will be a matrix. Then UR transpose times F times UR, can be pre-calculated because F is a constant. Then that's the reason why linear reduced model is much faster, is much more computational efficient. However, if F, let's say, is dependent, is Y dependent. Sorry about that. Okay, so then you won't be able to directly calculate this, reduced matrix in front of YR. Then what you need to do is you first need to, use UR to reconstruct the original solution, and then run this, reconstructed solution through nonlinear operator, and then project it back again. So that's the reason, why nonlinear reduced model is much computationally, it's kind of like a computationally inefficient in general. All right. So now I talked about, it's fundamental of the reduced models. The next thing is that, as I mentioned in the previous slide, we do need to have the UR, which is also called the POD modes. How can we get these POD modes? So in general, the POD mode calculation is pretty straightforward. So all what you need to do is that you run a snapshot simulation. Of course, this snapshot simulation has to be representative of the scenarios that will be simulated in the online stage, right? So basically, we know that when we run CFD or finite element simulation, you will have a 2D or 3D. But here, if you have but this is however, after you do this calculation, all what you need to do is that regardless of 2D or 3D, you just unfold all the solutions and then make them a single column vector. All right. In other words, I don't care about this is 2D or 3D, but eventually, after you get this solution, you will make them as a single column vector. All right. And the number of the elements in that single column vector is the dimension. All right. So for example, if I have 100 solution variables in this CFD model or finite volume model, then the vector will has a dimension of 100 by 1, right? So of course, I will collect a solution at a different time steps, right? So this T1, T2, Tn, that will be the number of the time steps, and then you put them together. This is called a snapshot matrix. All right. And the next step, what you need to do is you just perform a singular value decomposition. Of course, there are different ways to calculate the POD modes. All right, but here I'm just introduce the simplest one, the singular value decomposition. All right, and then you will have U sigma V transpose. All right, and this sigma is called a singular value matrix, which is a diagonal matrix. If you look at it, you will find that a lot of singular values on the diagonal of this matrix. These values on the diagonal represent the importance of each POD mode in U. Okay, U is, as I mentioned, that is the basis vector POD modes. All right. So then, this each individual sigma represents the significance or importance of each individual column. all right, in order to reconstruct the data or to explain the data variance, all right. So then basically here you can see, this is one of the example here. You can see that the value actually, decays. All right, that means the first one is the most important, the second one, the second important, and so on. All right, and then by evaluating these, singular values, you can determine how many POD modes or basis vectors you want to keep. So this process here, you can see that I have approximately equal, which means basically I want to do a truncation. Any POD modes associated with unimportant singular values will be truncated. All right. So then in that case, we will have a very tall matrix or skinny matrix UR, as you can see here. All right. That's exactly what we want, because if we have a tall or skinny matrix UR, then we can reduce the dimension of the original Y significantly. Okay. All right. So basically, another thing I really want to talk about is, here give you an example of the 2D airfoil, the U velocity. And here you can see mode 1, mode 2, mode 3, mode 100, and mode 20. And you can see that, basically, the low order mode is more important. And they basically capture the larger flow structure within this domain. However, when you go to higher order mode, you can see all these, very small, features that is used to reconstruct better of the solution locally. All right. Okay, I talk about the POD. The next thing is incremental singular value decomposition. So why I want to talk about this? Because if you look at my snapshot, hybrid snapshot simulation here, okay, basically, see here, okay, here I need to perform a POD. I have a POD. However, if I have another form simulation, I will generate more data. And then I need to use this new data to update the POD modes. Okay, right. So in other words, if I have another form simulation, I will keep adding new data into this POD mode. Then I need to update the POD mode, right? In other words, the POD mode in our POD modes in our hybrid snapshot simulation is not static. Okay, it needs to be updated on the fly. So now, that's the reason we need to use this incremental ISVD, all right? So now let's take a look at this. Let's say we already have existing data. This is added new data, all right? However, the existing data can be, decomposed or factorized using the singular value decomposition, as I introduced in the previous slide, all right? Now you have this new data, right? This entire matrix can be factorized in this manner, all right? Factorized in this manner, and here, okay, U transpose times tau n plus 1. That basically is the projection of the new data onto the existing POD modes, which is L here. All right, and this term basically is the orthogonal component, okay, of the new data with respect to the existing POD mode UN. Okay, that is J. Basically, this is the orthogonal component. All right. Of the new of the new data. All right. So then this matrix is orthogonal matrix. This matrix is also orthogonal matrix. All right. And then if you look at the Q here, Q of course is not orthogonal because you have L and K here. All right. And then basically, what we need to do is that because this is not this is not orthogonal, this is not a diagonal. Okay, then what we need to do is we just perform a singular value decomposition on Q matrix. Q is much smaller compared to this entire matrix here. We just need to perform, small, very cost efficient singular value decomposition on Q. All right. So after you do that, then you will have a U double prime, okay, and then the delta matrix, small delta. Delta matrix, sigma matrix, and also V double prime. All right. And then, so, the orthogonal matrix multiplied by another orthogonal matrix give you again, this is orthogonal matrix. All right. So by doing this, and you will find that eventually we will have this one, UN plus 1, and this sigma matrix, and also this V n+1 matrix. Okay, this one un+1 is orthogonal. Vn+1 is also orthogonal. All right, and then now in the middle I have this diagonal sigma matrix. Okay, that's exactly what I want. All right, that is basically is the singular value decomposition of the combined data. However, in order instead of running singular value decomposition, on this big matrix, we actually only need to do a small computationally efficient, singular value decomposition on this Q matrix. Okay, so then the computational cost to update this PUD model will be very low. All right, so we talk about the PUD. The next one is how about the switch? All right, so we talk about the full order model. I talk about the reducer model. The next question, how can we do a switch? All right, so in order to do a switch, basically, in the full order model, we only have the singular values. All right, so basically, we define the two number of modes. One is called RD, the other one is called RE. All right, so then we want to examine the energy ratio contained within these basic modes and the energy ratio contained within these extended modes. All right. So basically, if you look at it here, if this mode, the energy ratio can decrease very fast, that means this PUD has a high quality. It captures the solution subspace very well. All right. Then we want, basically, that's a good sign. And the second one is we also want to check the energy ratio within this extended mode. In other words, we want to make sure that even within that extended mode, the energy ratio, the signal values can decay very rapidly. That basically means that this PUD mode is very representative of the solution subspace. Okay, then we can switch this into a reduced model. All right, so then the next thing is that, okay, we know when to switch to the reduced model. The next question is that how do we know when we need to switch back to the full order model when the reduced model becomes inaccurate, right? So then in a reduced model, all what we have is the solution in the reduced domain, which is YR here, okay? So in other words, we need to examine the solution in the reduced space. So typically, because this PUD mode is orthogonal, all right. So then we can check the magnitude of this YR, and then to determine if the reduced order solution is still accurate or not. So let's say if the reduced solution in this extended mode, has a large value, then we know that, okay, this reduced model solution, basically, it will become less accurate because the high order mode start to take over, starts to become more dominant. That is not a good sign, because it indicates the reduced model becomes less accurate. In that case, we need to switch from reduced model to full order model. All right. So this slide basically presents our idea. How to determine the switch between full order model and the reduced model. All right. The next one is discrete empirical interpolation method. As I mentioned, the nonlinear reduced model, is not computationally efficient. Then how can we make it, computationally efficient? The DEIM is based on the idea of Geppy PUD. So basically, the Geppy PUD says that if this nonlinear term has a very good projection subspace, all right, and then when in order to reconstruct this nonlinear term at a different condition, you don't really need to calculate every entry, every entry in this nonlinear term. All what you need to do is that you can have a sparse measurement, at just a few discrete locations. All right. In other words, let's say, if this nonlinear term has a good subspace, let's say if I want to reconstruct one of the vectors here, okay, this vector, of course, I don't have. However, you only need to calculate the entries at a few locations. For example, here, 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 probably like, you only calculate their entries at the 3 locations, and then you can use Geppy PUD method to reconstruct the entire, vector. So then if that's the case, that of course, if you only need to calculate this nonlinear term at these sparse locations, the computational cost will be very low, right? So that basically is the key idea of the GAPI-POD and the DEIM. So the first step is, okay, we will also collect the snapshot matrix as I introduced previously, but this time this is for the nonlinear terms, okay? So let's say you have this at a different time. It's you have this vector which will represent your nonlinear terms within the domain, and along this direction that is basically represent a different time. Okay. Now you have this snapshot simulation. Snapshots of the nonlinear terms. Then you can perform a singular value decomposition. All right. You will get all these POD modes of nonlinear terms. All right. And then the key idea of DEIM is I want to see if I can use the next POD mode to approximate, if I can use the previous POD mode to approximate the next POD mode. So for example, this is my first POD mode, all right? Then can I use this, first POD mode? Can I represent the second POD mode using my first POD mode? Okay, at this discrete or sparse locations. That's basically exactly is the second step here. Okay. For example, if j equals to 1, then you see that this is the second mode. All right. And then this will be the first mode. All right. And of course, you should have a coefficient. All right. And then you want to calculate the residue. Okay, between the second mode and the reconstructed second mode. All right. This R2 means residue. All right. And then you check each element within this residue, and you see which one is the max. All right. And then if this one is max, then you want to basically kind of like determine this will be the location, which is very important, where you want to calculate your nonlinear term. Okay. And then we can go to the next iteration. In the next iteration, we will have 2 POD modes, and then we want to use these 2 POD modes to reconstruct the third POD mode at this, at this P2 locations. And then again, we can calculate the residue between the true third POD mode and the reconstructed third POD mode. And this is the R3 is the residue, and then you want to calculate, you want to find the location which has the largest residue element. Okay, that will give you the third location. So if you keep this, you will find a few important locations, and at this important location, you need to assemble or calculate these nonlinear terms. Once you have this location, the nonlinear term can be calculated very easily because this part can be calculated offline. In other words, during the online simulation, you don't need to calculate them again. They can be calculated before the ROM simulation. And only this part, if you look at this is the selection matrix, as I mentioned, this is basically this includes the location of important locations. So this basically shows that you only need to calculate the nonlinear terms at the important location. So if this one will be computational cost will be very low. This is already calculated offline or pre-computed. So then it's nonlinear term. The entire nonlinear term can be computed very easily. All right. Okay. So then after that, the next thing is the snap. However, we do have an issue. The issue is that so in our hybrid method, we only have a few terms are computed by the full order models, right? The next thing is how can we have enough snapshot? So here we used an approach. Okay, basically, the good part is that the subspace for the solution variables and the nonlinear terms are very different. So then we can use this method. The method is first in a full order model interval, and we have the full order solution. Then we will write through the nonlinear operator. We will get the snapshot of the nonlinear terms, and then in the reduced model interval, we will first reconstruct the solution in a full domain, and then write through the nonlinear operator, and then we will collect this reconstructed snapshot of nonlinear terms, and then we combine them together, and then we can perform a POD at the end of the snapshot simulation. Once we have this POD mode for the nonlinear term, then we can do DEIM, right? However, as I mentioned, there's a challenge associated with the DEIM, especially for the intercell transport term. The reason is that if you look at this transport term, the flux at the phase between two computational cells in final volume method, you will see that okay, it involves two solutions. One is the solution at the present cell, the other is the solution at the next the neighboring cell. All right. So then how can we address that? Because we do need to have the two solutions, in order to just assemble or calculate the nonlinear term for the present cell. So then, basically here you can see the steps. So step one, we will use DEIM algorithm to identify the interpolation cell or important cell P, okay, using the nonlinear POD modes. All right, that is basically this orange block. All right, and then the next one is we're gonna read the indices of all the phases enclosing the DEIM cell, which is basically these red boxes. All right. And then finally, indices of all the adjacent cells J connecting to the DEIM cell. Okay, once you have this phase, and then you can find their, the neighboring cells. Basically, this is the green blocks. All right, and then we only calculate, basically once we have this, then we will only calculate. We will calculate the nonlinear term in the DEIM cells using the solution at the adjacent cells and the DEIM cells. All right. So you can imagine, let's say this entire domain, is 5 by 5, 25 cells. And however, we only need to use the solutions from this green and orange blocks to calculate the nonlinear entries at the DEIM cell. Then, which is smaller than 25, right? Then this computation can be performed more efficiently. All right. So the next thing is that we will have some numerical experiments. And of course, this method can be applied to different physics problems. But here we just want to demonstrate this for nonlinear heat transfer. Okay. And very quickly, I want to give you a kind of like flow chart. How we do this all together. So let's say we have a continuous heat transfer equation here. And then this is a conduction. All right. And then this is the internal source term. And then if we apply the spatial discretization, then we will have this one. All right. Basically, let's say we only apply discretization to the spatial terms. All right. And then if we do this one for each individual cell, each individual cell in the computational domain, and eventually we will have an ODE set like this one. All right. And then you can clean them, and then you can organize them into a state space form, just like what we shown here. This A represents the conduction, but A will depend on temperature. That's the reason why we call it as nonlinear. Okay, so basically, that's the reason why you can see that here we have this A. This is the conduction term, but this is nonlinear. A depends on temperature. R is basically the is the coefficient for the radiation, which is another nonlinear term. D basically is the constant term. All right. Associated with the boundary conditions, and the B is called scatter matrix that basically can convert your input. For example, if you apply a heat flux at the boundary, and then that B will convert this applied boundary condition, the time varying boundary condition into the contribution to each individual computational cell. Okay, this B is called scatter matrix. Once we have the full order model, then we can do the reduced model. As I mentioned, we introduce this projection subspace or subspace projection. Then you will get this low dimension variable TR here. All right. However, as I mentioned, the ROM itself is not computationally efficient, so we need to use the DEIM. Okay. And here, basically, of course, DEIM. I already introduced the DEIM. Then we apply DEIM, we will get this ROM DEIM, okay? And all this term, and basically, this is from the DEIM procedure in the previous slide. And then this is the ROM DEIM in the final form. And here you can see that this QA is UR transpose times CA. CA is defined here. This part can be pre-computed. In other words, in the online simulation, you don't need to do anything about it, all right? This can be calculated before, and then only this part, the A, B matrix, and even this R matrix, you only need to assemble them and calculate them at those very important sparse locations. This one can be done very quickly. All right. So, and then here next, I will spend like a few minutes talking about the results. And here before that, I want to introduce some acronym about it. Okay, so here SS means that in a form that means the traditional snapshot simulation based on full order model. SS means a hybrid snapshot simulation based on full order model plus ROM. That is basically what we proposed here. FROM means a form reconstructed using the traditional method, and HROM is the ROM obtained by our hybrid snapshot simulation without DEIM. HROM DEIM means the ROM obtained by our hybrid snapshot simulation with DEIM at the end. All right. And again, we also have the verification simulation. Okay, here you have FROM. We will compare FROM, HROM, and HROM DEIM, and we will compare them in terms of both absolute error and the relative error here. All right. So the first case study is a multi-layer annular cone. All right. So basically, you can see that 3/4 of these lateral walls are applied. At here, 3/4 of the wall are given time-dependent heat flux. Okay, and then this purple one represents the input condition. For the snapshot simulation, and the green one basically represent the real heat flux at the lateral walls. Okay, and then the other boundary conditions are insulated. Okay, are use insulated boundary condition. And here we have the thermal conductivity and the density and the specific heat. We consider the time dependent temperature dependent properties and also constant properties. And then in this simulation, for the snapshot simulation, we have 480 seconds divided into 12 intervals. That means each interval is 40 seconds. For the online simulation, we also have 480 seconds. All right, the time step for the simulation is 0.25 seconds, and these are the coefficients used in the POD mode. All right, and then now let's see the solution. Okay, so here you can see that this is the 3D plot. Here this is the cell number, and this model has 9,408 cells, and here you can see that this is the cell number. This is the time, right? And you can see that as the time goes by, given this heat flux, and then the solution will increase rapidly, and then start to decay slowly. All right. And here you can see that it is hybrid snapshot simulation is very accurate to generate the snapshot data, because this is the full order model simulation, and here this is the difference between a full order model and our hybrid simulation. Okay, and you can see that the absolute error is less than 10K. However, the peak temperature is 800K. So that this error is very small. And then most importantly, 8 out of 12 intervals are simulated by ROM. And here you can see that all this are simulated by ROM. Only 4 intervals are simulated by full order model. So then if you look at this, our hybrid snapshot simulation is only probably 50% of the traditional high order full order model snapshot simulation. And then this one basically compares the full order model and the reducible model generated by traditional full order snapshot simulation, and the reducible model generated by our hybrid snapshot simulation. And again, you can see that both of them agree with each other very well. The absolute error is less than 12K, and considering this the peak temperature around 1000K, this error is very low, right? So the POD modes and the ROM generated using hybrid snapshot simulation is very accurate. And then this one basically shows the ROM DEIM with the DEIM approximation generated by our hybrid snapshot simulation. And again, you see that we have 40 interpolation cells, 60 interpolation cells, 80 interpolation cells. All right, this one does not have any DEIM interpolation at all. And however, if you look at this in general, okay, we can find that the absolute error is then 15K, and then you can see that this error definitely increase with the time, with the temperature. But however, in general, it's less than 15K, which means that this HROM DEIM is very accurate. All right. And then here you can see that this HROM DEIM, comparison with the full order model. And you can see that the error is less than 0.8%. All right. With only 40 interpolation cells. All right. And then here, the most important thing, you can take a look at this one. For the online verification simulation, if you use the full order model, it takes almost 300 seconds. If you use the reduced model without the DEIM, it takes 45 seconds. If you use our HROM with the DEIM, it only takes around 15 seconds, which is very small compared to the traditional methods. All right. This is the last case study. All right, we are talking about extended fin array. And again, basically here we have, at the boundary, the bottom here, we will apply a time-dependent heat flux. Okay, the purple is the snapshot. It's a step function for the heat flux, and then the green one is the verification, and then all the other boundaries are basically the radiation boundary conditions. And then for this one, we have 12 intervals, which each has 100 seconds, and the verification simulation has 960 seconds, and the simulation time step is 0.5 seconds. All right. And again, first thing we want to compare, in terms of we want to compare our hybrid snapshot simulation against full order model in the snapshot simulation, and you can see that the error is very low, which is less than 8K. Okay, and more strikingly, more interesting, you can see here, out of these 12 intervals, 10 out of them are simulated by reduced model. All right, and then the computational time is only half of the full order model simulation. All right, and then this one compare the reduced model generated by the traditional approach, which is FROM, and the HROM, the ROM generated by our hybrid snapshot simulation, and you can see that both of them agree with each other very well. The error is less than 1K, which is almost negligible. And here we also compare our ROM DEIM generated by our hybrid snapshot simulation with full order model using 50, 75, and 100 interpolation DEIM interpolation points, and here with this one without any interpolation. And you can see that although the error increases with time, but you can see that the error in general less than 1.5K, which again confirm that this ROM DEIM is very accurate. All right, so now let's take another look at the relative error. So in general, it's a relative error less than 0.12%. All right, using this DEIM ROM. And again, here, the most important is the computational time. So for this online simulation, full order model takes almost 800 seconds. But however, our HROM DEIM only takes 45 seconds. So you can imagine this is extremely fast compared to the full order model. Okay, and even the reduced model, the nonlinear reduced model without the DEIM. So DEIM is very, very effective in terms of cutting down the computational cost. All right, conclusion. So in this paper, we basically presented a methodology to construct the ROM DEIM using the hybrid snapshot simulation. We proposed the entire procedure or pipeline to streamline this hybrid snapshot simulation, including SVD, ISVD for POD, snapshot data accumulation, and the nonlinear DEIM ROM construction. And we only also talk about the reconstruction of the snapshot data of nonlinear term to address the issue of limited full order model data to apply DEIM. We also demonstrated how to develop DEIM for the cell-centered finite volume method. And then the computing performance is very impressive. All right, so we can reduce the computational cost of the DEIM ROM construction and improve the ROM efficiency, and along with adequate accuracy. So, for example, specifically in a hybrid snapshot simulation, we can improve the speed by 50%, And in the verification simulation, once the DEIM ROM it becomes available, this DEIM ROM only costs like a 5% computational time relative to the full order model. All right, and and only like 16% to 28% relative to the full order model without the DEIM. Relative to the reduced model without the DEIM approximation. Okay, that's kind of like all what I presented today. And this is basically, if you want to find out the details, please go to refer to the full paper, our full paper in the SN Applied Science. Thank you very much.
Okay. Thank you very much, Professor Wang, for the very useful and informative presentation. I actually learned a lot. It was complicated, I have to admit. I have to go back and watch the recording one more time, or maybe several times. And just to say it again, there will be a recording of this session on the journal website in a matter of few days. And you can, of course, I'm pretty sure, be in direct contact with Professor Wang if you had questions later on. But for the time being, something came to my mind that I want to ask you. You, somewhere between your slides, talked about updating the full order model on the fly, like learning from history of the system you're working on. And my question is more focused on the physical side of things, right? An example of mainly a phenomena that more variables are in play rather than only temperature. For example, we have a fluid flowing porous media where the media has a lot of uncertainty involved. So that's the fluid that we are dealing with. So when you want to update the prior, like the initial model that you have, do you, in such cases, have you gone that far to study that, or do you have any idea how to rely on this high fidelity full order model to have a kickstart to a as close to reality as possible simulation, and then go ahead with the reduced order modeling of cutting down on the complexities?
So the answer to this question first, for this physics-based model, we do not consider the uncertainty as you mentioned. If we have to consider the uncertainty, we have to go to other, stochastic PDEs, right? So this this is a reduced model approach, which is not specifically for the uncertainty. And then here, when we talk a lot about the updating, we are not updating the POD modes, according to the priors. Okay, this is not the approach we used here. This update is because the reason we want to update this POD mode, because when you have new data, new streaming data come into the picture, and then your POD mode will shift, the subspace of the solution will shift. Then we want to update that space of the solution, which is deterministic, by the way. Okay, so that's the reason why we have to introduce the update here. So again, to answer your question, this update is to correct or to address the shift in the solution subspace rather than for uncertainty.
Okay, fantastic. Thank you for your reply. We have a question from Dr. Thomas von Larscher. He asks about the hybrid snapshot simulation method, how to define the optimal time interval. I think one of your beginning slides, you talked about the interval that you choose to break down the whole interval. So it certainly depends on the problem covered, right? What if the problem is highly nonlinear? Is there a global optimal time interval for that?
That's a very good question. So basically, this is the early work of our hybrid snapshot simulation. So at this moment, this interval size is fixed. We basically determine it at the beginning. All right. So actually, we are also working on approach right now, and actually we will also present some work in the. I have another conference paper in August that where we can use we develop the criterion to determine the interval length adaptively. All right. In other words, by monitoring these arrows or the POD modes, the singular values, and also the POD mode coefficient in the reduced domain, you don't need to fix the length of this interval before the simulation. You can actually on the fly determine this length, okay, by monitoring the errors. So to answer your question, for this work, we don't have an optimum interval length. It's a fixed. But okay, you should be able to extend it by monitoring the singular values and also monitoring the POD mode coefficient in a reduced domain. Then you can have an adaptive length of interval.
Okay, great. Thank you very much, Professor Wang. It was very useful, very informative. We really appreciate your time joining us today. We don't have any more questions from the audience. Thanks, everyone. I hope you have a good rest of the day. And Professor Wang, if you in the future wanted to join us again, it was really enjoyable. You can actually be at your service. I think we have one last minute. Somebody is thanking you directly. Thank you very much, everyone. Have a good day. And we are closing the session right now.
Thank you very much.
Thank you. Yes, bye-bye.